So standard enthalpy of formation, and that is delta H with a lowercase sub f, f standing for formation. And then you see this knot at the top. That means that in this case it is under standard conditions. So standard enthalpy of formation is the change in enthalpy that accompanies the formation of 1 mole of a compound from its free elements. So every element that makes up that compound, to make 1 mole of that compound is the delta H, the standard enthalpy, when it's in the standard state. The delta H formation, so the delta H formation of free elements, so anything that's on the periodic table or your diatomics, is 0. Because it's not really being formed from anything. So it's 0.
You said those were the diatomics?
Your diatomics or anything that's on the periodic table.
Or just anything?
So yes.
Okay.
So yes.
Oh, that makes sense.
Okay. So next, just your standard states. Just for a gas, standard state is the pressure is 1 atmosphere, a solution is 1 molar, and then for an element, it would be at 1 atmosphere, 25 degrees Celsius. Those are your standard states. So the heat of formation, like I said, so if you see these equations right here, there's 3 equations. And the heat of formation for water, and we see that it's 1 mole of water, 1 mole of HCl, and 1 mole of magnesium carbonate. Each one of those, the standard formation, it has a value. And that is in kilojoules per mole of whatever we're making. Okay, and like I said, free elements have standard, their delta H is 0. And then if you weren't given this number, you'd go to a table and look it up and you would find it. I will tell you that states of matter also take into consideration, because for the HF for water liquid is different than for water as a solid. So you have to make sure you get the right state of matter. All right, so I want to form CH4. And we want to have 1 mole of it. So what makes up CH4? What elements? Carbon and hydrogen, H2. And then we go and we are going to balance that. So we need a 2. One thing I forgot to say, what do we see here that we've never seen before? Fractions. So when we're talking about heat of formation and equations for combustion, fractional coefficients are okay. We will never see fractional coefficients unless it's in combustion, heat of combustion, or heat of formation. So now let's make one more thing. Let's make a mole of calcium phosphate. So what elements make up calcium phosphate? Calcium. And how many calciums do we need? 3. What else do we need? Phosphorus. And how many phosphorus do we need? 2. And lastly, we need oxygen. And how many? O2. And so how many O2s do we need?
4.
4. Okay? So we're not talking about ions or anything else. We are talking straight elements. Free elements. Any questions on that before we start doing some of these? Okay.
Why do we do that?
Huh?
Why?
I just want to show you, if I say, what is the equation, write the heat of formation of CH4.
So the equation is the heat of formation. It's not.
The heat of well, write the formation, heat of formation equation
Okay.
of CH4.
Okay.
We're just practicing writing formations. Yes. The next thing we have is enthalpy of combustion. So delta H, and it will say instead of sub F, you have sub com for combustion. And the enthalpy of combustion is the amount of heat produced when 1 mole of our substance is combusted. So when we do the heat of formation, what we're interested in is as a product. But here, when we are doing heat of combustion, our substance is going to be the reactant. Okay? So let's combust methane. Yes? Mole. We are going to combust methane. And we're going to combust 1 mole of it because that's what delta H of combustion is. So what is the equation for combustion of methane? No, combustion of methane. We're going to take methane, and to undergo combustion, what does it have to react with? So it's going to react with oxygen. And what are the 2 products we're going to make?
Water.
Water and CO2.
You'll always make water and CO2. Right?
You always make water and CO2. Okay. We need to balance this. When balancing this number in front of CH4 or in front of our substance that we're combusting must always stay as a 1. You cannot change that. Per the definition of delta H combustion.
So we just put a 2 in front of water?
Yes. So we need a 2 in front of water. And now I always put oxygens last. So how do we
2.
Put a 2 in front of O2? And that's it. All right, this time, let's combust. Yes?
In combustion, are the only products going to be water and So there's not going to be anything else?
Now let's combust this. What's it going to react with to undergo combustion? Oxygen. And the 2 things we make? Water and carbon dioxide. And now we have to balance it. We cannot mess with our C3H7OH. It has to stay with a 1. So go with carbons first. 3. Next, do your H's. We have a total of 8 H's. So we need a 4. And now we have a total of 10 oxygens on one side and 3 on the other. If I have one oxygen And then I have to, whatever I put over there, I have to multiply by 2. Whatever I'm putting over here has to be multiplied by 2. And then add them together has to get me to 10. So what is that? Now I need 9. So it's going to be 9 halves.
I forgot.
Somebody told me a while ago 4.5. 4.5, but we want the fraction. So what should be 9
So
over
we
2?
don't like decimals?
No.
I feel like decimals are the ghetto version.
All right, any questions on that? Okay, so let's go do some problems. The flippy thing, which is really, the flippy thing is us manipulating these equations so that we can get to our end-all goal. Our end-all goal is right here. We have these heat of formations for these two reactions, and we need to take these reactions and we need to manipulate them to get our goal, and then figure out what the delta H is going to be at the end. So the very first thing, this should not be new to you. We've manipulated equations before. How can I take those two equations and make my overall goal? I go to the first equation and look and see. I need to flip it because I need CO as a product or reactant. So CO, C plus 1/2 O2. If I flip it, which means it was exothermic, now it becomes endothermic. So now the delta H becomes positive 111. What do we do with the next equation? We leave it alone. So we have C plus O2 gives me CO2. The delta H this time is going to be left alone, 394. Always double check to make sure that your equation you've got your goal. So my C's go away. I have half an O2 that goes away, which leaves me with a half an O2. So CO plus 1/2 O2 gives me CO2. So my goals match. And now what we do with our delta H's, if we were in kinetics, we would multiply them, but this time we are going to add them together. And the delta H for this reaction is going to be negative 283 kilojoules. Should have seen this in pre-AP. It was a very fast lecture in my class, I know.
It was 2 years ago. So, yeah. That's why I don't remember a lot.
Yeah, well, Marcus told me that his teacher kind of sucked last year, so.
I liked Miss Boyle.
Which is me. I said, well, okay, I'm sorry about that.
Our class didn't learn much, though, because we had like Dawson and AJ and every other annoying boy.
Okay, now we have the following. Using the following standard enthalpy of reaction, calculate the heat for the combustion of 1 mole of ethane. It does not give me my goal. So we need to come up with our goal. So we're going to take ethane, C2H6, and we're going to combust it, which means we're going to add oxygen, and we're going to get carbon dioxide and water. We cannot mess with the carbon, or the ethane, so that means I need 2 carbons. I go to my hydrogens, and I need 3 waters. And now we have a total of 7 oxygens.
7/2.
7/2. So that's our goal we have to make. So let's start manipulating. So first one we're going to flip. So C2H6 gives me 2C plus 3 H2s. We flipped it, which means my delta H is now going to be positive 84.68. All right. Next, what do we do with the next one? We need 2 carbon dioxides.
Leave it. Oh, wait.
We only have 1 carbon dioxide in that original equation. So we need to double it. So we're going to multiply everything in that other equation by 2. So we have 2C plus 2O2. And that's going to give me my 2 CO2s that I need. Delta H also gets multiplied by 2. So it's going to be 2 times negative 394, which is negative 788. Thank you. The next one, look at your waters. What do we need to do with the waters? What do we need to do with this equation? Multiply it by 3. So 3H2 plus 3 halves O2 gives me 3 waters. My delta H, again, is multiplied by 3.
Negative 858.
Thank you. Gives me negative 858. Before I go and I get those together, I'm going to make sure I get my overall goal. My H's go away. My C's go away. I have a whole number and a fraction. So if this is 4 halves, then that makes 7 halves. So that's good. My ethane is good. And then our carbon dioxide and our water is good. So now we add our delta H's together. And what do we get?
Negative 1561.32.
I'm just going to go 1561 kilojoules. Everybody good with that?
How did you, wait, okay, you have the 3 halves for your oxygen, plus 2.
Plus 2, so I've turned the 2 to a fraction.
4 over 2.
Okay.
Wait.
Oh, sorry. I'll go back. There you go.
Okay. Negative 1. Okay, we're good. Thank you.
All right, so next we're going to talk about Big Mama. And Big Mama says that the heat of a reaction can be determined by adding together the enthalpies of formation associated with a series of formation reactions that generate our reaction. So the delta H can be determined by taking the sum of the heat of formations of our products, and we subtract the sum of the heat of formations of our reactants. Products minus reactants. All right? So the sum of products minus reactants is Big Mama. So we're going to solve these. It looks like it's, oh, well, yeah. Okay, so here is our reaction. And I look at it and I say, oh, they've given us heat of formations. I got to use Big Mama to determine this. So Big Mama is going to be delta H is equal to the sum of the H of my products minus the sum of the H of my reactants. I start getting lazy and the sigma goes away. So now the thing is start doing your numbers. So delta H is equal to my products. I have NaOH as a product, but how many products do I have? 2. So 2 times the formation of NaOH, which is negative 470. And then I'm going to add to that, I have 1H2. The heat of formation for any free element is 0. And then from that total, I'm going to subtract the total here. And that is 2 times the sum or the heat of formation of sodium, which is 0, plus 2 times the heat of formation for water, which is negative 286. So do what you have to do to get that into the calculator and get me an answer to 3 sig figs. Negative 368. And that is kilojoules per mole of the reaction. Any questions on Big Mama? We're going to do one more. I think 2 more slides and then we're done. Everybody good? Okay, so here's some information that was left out of here that we need to write. I need to give you the delta H's for these. So for C2H5OH, it is, and this is going to be kilojoules per mole, negative 278 for CO, and that's liquid. For CO as a gas, CO2, it is negative 393.5. And for liquid water, it is negative 285.9. So that's our information. Now it wants to calculate the delta H for that reaction. So delta H of the reaction is sum of the products minus the reactants. So 2 times CO2's value, which is negative 393.5, plus the 3 from water, which is negative 285.9. I'm going to subtract from that the C2H5OH. I only have one of them at negative 278, plus I have 3 oxygens with a 0 heat of formation, and that will give me my delta H of the reaction. Give me 4 sig figs.
348.
Mm-mm.
Negative 1366.
Negative 1366, 67 kilojoules per mole of the reaction. I always just put my delta H reaction over, I just put the reaction on my delta H. You don't have to put it, at least per mole though. Okay. Y'all ready to do the last one where we're solving for something within the product or reactant side? So we're going to come back to these HF numbers that we just had. So we're coming back to these numbers. So let's do this. Now we have the standard enthalpy of combustion for cyclohexane. So we know that the delta H of combustion for cyclohexane is negative 3924 kilojoules. Calculate the standard heat of formation of cyclohexane. So that is going to be my X. I need to figure out what that is. So delta H is products minus reactants. Delta H is negative 3924. They've told us that. Combustion. Yeah, it would be for 1 mole of that. Yes.
No, like the units.
Yep, kilojoules per mole. So now we have product, CO2. We have 6 of them, times negative 393.5. We're going to add to that our 6 waters, 285.9. We're going to subtract the sum total of our 1 cyclohexane, which is my X, minus 9 times 0. So negative 3924, and I know it's just extra math. I'm just showing the steps. You could have just left that out. Negative 4076.4 minus X. So 152.4 is minus X. Therefore, X, the heat of formation, which is the heat of formation for C6H12, is positive 150, or negative, sorry, negative 152.4 kilojoules per mole. Any questions? I highly suggest to go home and work those problems for the homework and come Monday with questions.